This lesson, we're going to look at system word problems, and specifically, we're going to look at word problems that are types of mixtures. So we have looked at basic system word problems. This is going to take these a little bit further and look at that specific kind called a mixture. So mixtures are word problems that have a percent or a monetary amount in them. Monetary means money. So you're looking at dollar amounts, percentages, percents of substances. So if you see a word problem that's dealing with percentages and even monetary or money amounts going with each variable, that's a mixture word problem. When we encounter mixture word problems, one equation should be the totals of the variables. So one equation will always be your totals equation, representing this plus that equals a total. The other should show the percent or money with each variable. So, for example, we have 8 dogs plus 3 cats equals 11 animals total. And then if we're told dogs are being sold, I don't know, for $10 per dog and cats are $5 per cat, then the total amount on that equation, we're multiplying each part. So 8 times the 10 and whatever I said, 8 dogs, 10 cats, whatever, times that money amount per animal, that will equal a total money amount. So we're always looking for one equation to be a totals equation and the other equation to be a money or percents equation. So I do like to label my equations as I'm setting them up. One is the totals and one is the money or percents equation. And that'll set up the system that we can then solve. So to set up and solve mixture word problems, where the parts equal the whole. So these portions of the equations make up your parts. And obviously what it's equal to is your whole amounts. So we'll be looking for certain keywords like these as we go through word problem mixtures. So let's take a look at our first example. A metal alloy is 25% copper. Another metal alloy is 50% copper. How much of each alloy should be used to make 1,000 grams of a metal alloy that is 45% copper? Before we get into this mixture problem, what I want you to understand about chemical mixtures is even if you don't know what a metal alloy of copper or percentage of copper is, you can still do this word problem. It doesn't matter if you're not fully aware or understanding what's going on chemically in this situation. But I do want you to think about this in a different way. So I like to think about this like orange juice, okay? We can buy two kinds of orange juice. Well, several kinds of orange juice, but let's bring it down to two. We can buy a type of orange juice that is very full and has lots of pulp in it. Right? Some people love orange juice with pulp, others not so much. And you can buy orange juice that has little to no pulp in it. So think of these as your different metal alloys. Another metal alloy is 50% copper. This one would probably be the closer to 50% copper alloy because it's got more of the pulp in it. And this one, this orange juice would represent the 25% copper alloy where we're having way less pulp than the other one. And if you were to take these glasses of orange juice and pour them and mix them together, you're going to get a new glass of orange juice that falls somewhere in between the pulp levels of the original two. Oh, let me get this to go away. Sorry. Okay. Anyways. Okay, so somewhere in between, if we mix these two mixtures together, and that's why it's called a mixture, we could get a type of orange juice that has 45% pulp rather than the 50 or the 25%. We'll find something in the middle. And you can try this at home. You could take something with tons of pulp in it, something with almost no pulp, mix them, and you're going to find you get a some pulp mixture of orange juice that you can buy at the grocery store. So think about this problem like that. So let's come back to the metal alloy, copper alloy problem. What are we trying to find? So here the question says how much of each alloy should be used to make the 1,000 grams. So we're looking for how much of each alloy. So how many grams is that how much part of each alloy is what we're looking for. So let's identify our variables. Let's name X as the number of grams of the 25% copper alloy and Y as the number of grams of the 50% copper alloy. Again, X and Y you can determine, but that's why we always identify variables first. That I'm just choosing there, okay? But we are looking for how much of each of those. Now comes setting up our two equations. So if you'll remember, we should have one equation that just represents the totals and the other that represents the percents or monetary amounts. Now in this example, we're dealing with percents, so we'll get to that in a moment. For the totals equation, we're finding out together to make 1,000 grams. That's answering how much is a grams of. Okay, so this 1,000 grams total should find itself, we should find it in the totals equation. So however we add these together, it should equal 1,000 grams. So I'm going to set my totals equation equal to 1,000 because I know that the two types of mixtures, however much I have of each, it should add up to be 1,000. Now we named X as the number of grams of the 25% alloy and Y is the number of the grams of the 50% alloy. So in the totals equation, I should add X and Y together, their amounts of grams, and that should total the 1,000. Usually you'll find your totals equation is often the easier one to write. From here, and I do recommend writing your totals equation first, specifically because the next equation usually comes from it. From here, we want to set up a percentages equation. Now, X is the number of grams of a 25% alloy. So however many grams of that, or copper alloy, so however many grams of that metal alloy there are, 25% of those grams should be copper. So to calculate that, we're going to multiply X by 25%. And when we do that in an equation, we should convert that percentage to a decimal. Of the Y variable, that represents the number of grams of the 50% copper alloy. So we've got this whole glass of pulp, right? But 50% of it is the copper alloy. So to calculate how much of that glass is the, pulp orange juice or whatever it might be, we're going to do 50% or 0.5 in the equation times Y. Now, here's the last part where we have to calculate the new total. Because whatever we get, we want the final total amount to be 45% copper. So we know that we want the weight or the amount of that total to be 1,000 grams. But of the 1,000 grams, we want 45% of it to be copper. So here we're going to do 45%, 0.45 times the 1,000 to find the total of our percents equation. And these are the two equations we'll be using for this word problem, this mixture problem. At this point, we're going to go ahead and we just have a system that we can solve. So you would simplify 45% of 1,000, so 1,000 times 0.45. And from here, we just solve our system. Hopefully you're seeing X and Y are already close to being isolated, so you could easily just isolate X and use substitution to work out this problem. You could also use elimination here to multiply this equation through by either 0.5 or 0.25 to get either your x's or y's to have the same coefficient, and that will cancel out. So that choice is yours. Take a moment, solve this system, click pause. When you're ready to check, click play. Okay, so you have solved your system. And just check that you should have gotten x to be 200 and y to be 800. Again, going back to how we identified our variables, x stood for the number of grams of the 25% copper alloy. So we should say of that one, there's 200 grams, and then of the 50% alloy, we had 800 grams. And so we've now figured out the quantities of each of those different alloys that when we mix them together, they produce a 45% copper metal alloy. And they do total the 1,000 grams we were expecting them to total. Okay, let's move on. Here's our next mixtures problem. Susan wants to mix Virginia peanuts that cost $3.50 a pound with Spanish peanuts that cost $3 a pound to obtain a 10-pound mixture that costs $3.40 a pound. How many pounds of each peanut should she use? Right there in that question at the end, that's answering what we're looking for. How many pounds of each peanut? Well, we've got Virginia peanuts and Spanish peanuts. So when we are setting up our variables, we should name one as the Virginia peanuts costing $3.50 per pound and the other as the Spanish peanuts costing $3 per pound. So I have named my x as the number of pounds of the Virginia peanuts at $3.50, $3.50 per pound, and y is the Spanish peanuts. Okay, from here we need to set up our two equations. If we go back and reread that problem, you can see that we are trying to obtain a total 10-pound mixture. And notice that the units for x and y, they are number of pounds. So the totals equation, everything in it should have a units of pounds. So when I add x and y together, the pounds of each type of peanut, I should finish with 10 pounds total. That's what was given to us in the word problem. From here, we need to now calculate, okay, how much per pound we're going to be paying. So if we know that x is the Virginia peanuts costing $3.50 a pound, you can think about this logically. If it were 2 pounds that we were buying of Virginia peanuts, then you would have to double the $3.50. That would be $7 total for 2 pounds. So really what we're doing here is multiplying the amount per pound. And if we want the result, the end result, a 10-pound mixture to be $3.40 per pound, then we need to still calculate that amount as well. And so here we have our two equations, the totals equation representing the total number of pounds of each, and then the monetary equation representing how much per pound. You can see we recopy, we still have our structure, x plus y plus 10, but in the second equation we're multiplying each by its monetary amount. We can now solve our system, so like we did with the last one, take a moment, solve this, solve for x and y, and state your answer with units. When you're ready to check it, click play after pausing. All right, so you have solved your system and hopefully found 8 pounds of the $3.50 Virginia peanuts and 2 pounds of the $3 per pound Spanish peanuts. Okay. So our next problem. John Craig invested a portion of $15,000 at 10% interest and the balance at 6% interest. The balance really means the rest, the remaining amount. So you can think of this as the rest. The rest of the money went in a 6% interest account. If he earned $1,260 from the interest of the two accounts, How much did he invest at 10%? All right. This one is slightly different. It's still similar. We're going to have a totals equation and a percents or monetary amounts equation. But there will be a slight difference that I want you to look out for. So John Craig invested a portion of $15,000, and we're wondering how much he invested at the 10%. So we are going to need to identify the variables as amounts of money at 10% and at 6% interest. So I've named my X as the amount of money at the 10% interest account and the Y as the amount of money for the 6% interest account. We are told he invested $15,000 total. So a portion of it went to the 10% and the rest at the 6%, but the total amount that we're dealing with here is $15,000. You will see a second kind of end result monetary amount, and we'll come to that in a moment, okay? But our totals equation, we're going to name the amount of money we put in the one account plus the amount going to the other account should total $15,000. Okay? From here, we are going to calculate, okay, if, let's say we put, I don't know, $10,000 at the account earning 10% interest, then to figure out how much money we're earning on that account, we would multiply 10,000 by 10%, and that percentage amount tells us how much extra we're getting from that account. So to calculate this, I'm going to write this as 0.1x because it's 10% times x. The Y account, remember when you're converting to a decimal, move it 2 places. So plus 0.06y. We're still following the structure of our totals equation where we have the x plus the y. But this is where there is the slight difference. In both previous examples, we just copied the 15,000 and multiplied it by its percentage or whatever the scenario called for. In this problem, though, notice you aren't given a third percentage. You're not told the percentage earned on the total amount here at the end. What you're told is actually how much money was earned at the end from the two accounts, and that's that $1,260. So the slight difference here is that this second equation is just equal to 1,260. In the previous equations, you were having to calculate this percentage or monetary amount. You were having to find that. In this problem, that money or amount is given to you, so you don't have to do any percentage calculation. So if you're missing a third percent in your problem, that's probably a hint that the new money amount's been given to you. So here is our system. Take a moment, solve it, find x and y, and state your answer with units. Click pause when you're ready to check. Click play. Okay, so let's check this word problem. We should have found that $6,000 was invested in the 6% interest account and $9,000 went into the account earning 10% of that amount. And then from that, you're making the total 1,260 that we were told. Okay, we have one last example problem. Similar to the chemical copper alloy problem we saw earlier. A 20-ounce alloy of platinum that costs $220 per ounce is mixed with an alloy that costs $400 per ounce. How many ounces of the $400 alloy should be used to make an alloy that costs $300 per ounce? So we are looking for how many ounces. So this tells you what our variables units are. So X is going to stand for the ounces of the $400 alloy, and Y would stand for the ounces of the $300 alloy. Oh, this is not the same example that I have. Anyways, sorry. Okay. What's slightly different about this one that I want you to notice is that you are actually told that a 20-ounce alloy costs $220 per ounce. And that is mixed with an alloy that costs $400 per ounce. Those two are the ones being mixed together, but we're trying to find the total in this one. We're trying to get one, that costs $300 per ounce. That's what we're trying to find. That's the end result outcome one. So this problem has kind of taken our two equations a little bit further, where we are actually given one of the parts. Remember, these two pieces are your parts. And we are actually looking for the whole. We don't know how many ounces of that final $300 per ounce alloy we're going to get that will qualify for this scenario. So that's why I've set X and Y still as the ones I don't know about, the ounces of the alloy we don't know. But the one that we do know is actually not the end result total. So we're taking a 20-ounce alloy of platinum that costs $220, and we're mixing it with the alloy that costs $400. Well, that's our X, because that's how we named it. So we are mixing the 20-ounce alloy. The totals is ounces of, so everything I'm putting in my total equation should be a unit of ounces. So I'm mixing the 20 ounces with however many ounces of the $400 alloy, and it should equal the number of ounces of our end result product we're looking for, the $300 per ounce alloy, and that's actually our Y. Everything in our totals equation has a unit of ounces. The difference is that the actual total is the piece we're looking for. We were given one of the parts we are mixing, and we know that from that first sentence where it tells us we are mixing it with the $400 per ounce alloy. From here, we should still be able to follow that similar structure where we keep each piece the same in our new equation, but multiply it by its monetary amount. So the the 20-ounce alloy of platinum that costs $220 per ounce. We are just told that, so we should be multiplying 220 by the 20, then the $400 per ounce mixture, we multiply per ounces of X. We don't know how many there. And then for the total, we're doing 300 times the Y, the amount that we, again, don't know there in the total. But we do know how much each of these should cost per ounce. So each of these gets multiplied by a dollar amount. Okay? And now those are our two equations. All right, from here you can solve it. When you're ready to check, click play after pausing, and we'll check our answers together. Okay, so hopefully you used substitution because Y was already isolated right here. So all we had to do was take this and replace Y with it and distribute and solve. That left us with X being 16 and Y being 36, meaning that we needed to, have 16 ounces of the $400 alloy to be mixed. So X of 16 is really the one that we absolutely needed because that's what it was specifically asking for. But there were 36 ounces total at the end. Okay. One last chemical mixture problem because these are usually the toughest ones. So we'll do this one together as well. A chemist needs to mix a 12% acid solution with a 32% acid solution to obtain an 8-liter mixture consisting of 20% acid. Notice we are given 3 percentage amounts, so that's telling us we're probably going to have to calculate a percentage total. But we're being asked how many liters of each of the acid solutions must be used. Well, the how many liters tells you the units for your totals equation. So when you're setting up your variables, we're trying to mix a 12% with a 32%. One variable should represent the amount of liters at 12%, and the other variable should represent your amount of liters at 32%. So I've named X as the liters of 12% acid solution and Y as my liters of 32% acid solution. We are trying to obtain, which means to get, to end up with an 8-liter mixture. Well, right there is the total liters we want to end up with. So I can fill in, I know the total, I don't know my parts, so I can fill in X plus Y equals 8. From here, we have our 3 percentages. We know the total N mixture should be a 20% acid solution. So that means that one gets 0.2 times 8. The X was 12%, and the Y was the 32%. My equations get a little crammed. I need bigger boxes. But anyways, those are our 2 equations for this system. You can now solve it. Click play when you're ready to check. Okay, we should be getting X to be 4.8, Y to be 3.2, telling us how many liters of each we'll need for this mixture. So again, this one we were given the total amount of liters. We didn't know the parts, so that followed the basic structure we were following for most of the examples today. Do look out for when you're given one of the parts and you're looking for the total. That one we just saw, last example, that's going to be probably the little more rare, but just something to always be looking out for. That can happen in these problems. And that concludes the mixtures lesson for systems.